I'm Mark Arenies, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. We begin in the top left corner of a grid and can only move to the right and down along the grid line. Our task is to count how many distinct paths there are that get us to the bottom right of the grid. The problem description shows us all of the paths in a 2x2 grid, and then asks us to count the same for a 20x20 grid. Let's see a few examples on a 3x3 grid. One simple path through a 3x3 grid is to move right as far as possible and then down from there. We could also move right 2, then down 1, then right to avoid the corner. Or we could go right twice, then down twice, then take our third right and then down. Or right twice, all the way down, then out to the right. If we choose to go right once from the start, then we move down 1, and at that point we have a 2x2 grid to cross. We already know all 6 ways to do that. If we go right first, then there are 10 solutions. And since this is a square, going down once will produce the same number of solutions by symmetry for a total of 20. There are a couple of different ways to look at this problem, but first let's approach it directly. We'll start our draft this week with a bit of Lua. At a given point on the grid, the information we need to have is how far we are from the goal position. To that end, we're going to write a recursive function that counts all of the possible paths from our current position to the goal. First, every good recursive function needs a base case. If we're already on the far right of the grid, then we only have one option. No matter how far we are from the goal, if we're on the far right, we can only move down repeatedly. So if x is 0, then there's only one path. Likewise, if we're already at the very bottom of our grid, then the only option is to move right repeatedly. So if y is 0, then likewise, there's only one path. Otherwise, we have two options, right and down. If we move right, then x decreases by 1. If we move down, likewise, y decreases by 1. In either case, we call our function recursively, then we sum the results of the two paths, and return. We can check this function on small inputs. For the 2x2 case, it produces 6 as indicated in the problem description. And a moment ago, we enumerated 20 possibilities on a 3x3 grid. And likewise, we can verify the result by calling this function with 3 as both arguments. However, this function is not nearly efficient enough to calculate our real solution in a 20x20 grid. In general, every call to our function will make 2 recursive calls with slightly smaller arguments, which means this function grows exponentially in the size of its arguments. There are a few ways we can solve this. First, let's discuss the problem from a combinatorial perspective. There were 20 paths through the 3x3 grid, which we enumerated by hand. If we look at these paths, we can see some patterns. For one, every single path had length 6. And in each path, we moved right 3 times and down 3 times. The only difference was the order in which those moves happened. This makes sense, for if we start 3 away from our goal in the x direction, then clearly we have to move right 3 times to get there. And likewise, if we're 3 away in the y direction, then we must move downward 3 times to get there. So in essence, the problem for a 3x3 grid can be reduced to this. We have 6 moves, and 3 of them must be right movements. Choose all of the ways in which this can occur. Now you may recall that a few weeks ago we discussed the binomial coefficient, written as n choose k. The binomial coefficient returns the number of distinct ways to select k balls from a bucket of n balls. But it doesn't have to literally be balls from a bucket. The k balls can be moments in which we move, and the buckets can be rightward movements. So we can rephrase the problem as follows. The binomial coefficient returns the number of distinct ways to select when we take our 3 right movements, given that we have 6 moments in time in which to do so. That is, the 3x3 grid traversal problem can be counted very efficiently as 6 choose 3. We know a couple of ways to calculate binomial coefficients. One is Pascal's triangle, but perhaps the most straightforward is using the explicit formula in terms of factorials. N choose k is equal to n factorial divided by the product of k factorial and n minus k quantity factorial. So 6 choose 3 is equal to 6 factorial divided by the product of 3 factorial and 3 factorial. 6 factorial is 720, and 3 factorial is 6. All in all, this simplifies to 20 as intended. We can extend this readily. To get across an x by y board, we need to make x plus y moves, and x of them must be rightward movements. So the solution in general is x plus y choose x. Let's write it in Lua. First, we write the factorial and binomial coefficient function. We've done these before, so I won't dwell on them too much, other than to point out that Lua, like Python, uses 2 forward slashes for integer division. Our possible roots function simply calls our choice function, and once we call the function, we get 0. This program still doesn't quite work. Lua stores integers using a 64-bit representation, and while the eventual solution to our problem fits in 64 bits easily, the intermediate calculation of 40 factorial exceeds that by several orders of magnitude. If we want to use a combinatorial solution, we'll need a language that has support for arbitrarily large integers. So let's hop over to Raku for a minute. Raku is a relatively recent language based on Perl, and it combines several paradigms in unique ways. We've used Raku before, so we'll go over this quickly. Our factorial function can be written quite compactly. We generate a sequence from all the numbers from 1 up to n, and then fold the multiplication operator over it. Our choice function is nothing too unusual. The forward slash in Raku is so-called true division, and integer division is done with the div infix operator. Finally, we write our possible routes function and call it. Now we can actually make this code a bit prettier. Raku puts a big emphasis on customization and reflection features, and the parser is incredibly capable. So let's take advantage of that. Mathematically, the factorial function is usually written as a postfix exclamation mark. Raku already defines the prefix exclamation mark operator to perform Boolean negation, similar to many other languages. But fortunately for us, there's no reason we can't have a postfix and prefix operator with the same symbolic representation. We define our factorial function with the somewhat unique name postfix:bang, which allows us to neaten up our choose function and make it look more like its mathematical counterpart. We can even replace the star with an actual Unicode multiplication symbol if we feel so inclined. While the binomial coefficient operator is usually written as two numbers atop one another, it's also not uncommon to see it written as an infix capital C, and we can represent it as such in Raku by naming the function infix:C. We have a solution in Raku, but let's try another tactic and see if we can solve this efficiently without resorting to the rather unfortunate 40 factorial calculation. Our original naive solution was actually quite close to something viable. We had a recursive function of high complexity that broke a large problem down into smaller ones, and that function ends up getting called with the same arguments many times over the course of the computation. We've seen this problem before, and the solution was dynamic programming. That is, we're going to cache intermediate results. We'll create a global variable called cache, which is equal to a newly allocated table. Tables are a sort of Swiss Army knife in Lua, functioning as key-value dictionaries, dense or sparse arrays, and objects in the sense of object-oriented programming, all in one data type. Inside our function, after checking our base case, we check if the x and y values we're currently at are in the cache. If so, we use the cached value. If not, we do the computation and store the results in the cache for later. Note that we stringify our cache key. Technically, any Lua object can be used as a table key, so it seems like we should be able to use an array, or rather a table, of x and y. Unfortunately, that's not quite the case, as Lua compares table keys for equality using raw equality, which considers two tables equal if and only if they're the same object, not just if they contain the same values. So we'll use strings, which have an equality operator more conducive to our particular use case. Now we have a working Lua program that runs instantaneously and doesn't require excessively large integers in the intermediary. We're ready to move on to the language of the week. This week, we'll be working in Prolog, specifically SWI Prolog. Prolog is the most well-known logic programming language. Logic programming, as the name implies, is a programming paradigm with roots in formal logic theory. In a Prolog program, we phrase our code as facts about a particular domain model, and then we phrase our eventual computation as a question about that domain. Prolog, in effect, uses logic to determine the answer, given the facts in question. One immediate consequence of this is that we do not assign values to variables. Instead, we simply assert logical statements that happen to contain variables, and Prolog will fill in the values as needed using a process called unification. For example, if we want to get the length of a list in Python, we would call the len function on that list and presumably assign the result of that call to a variable. But there's no len function in Prolog, primarily because there's no such thing as a function in Prolog. Prolog is based off of predicates, which are simply assertions of truth and don't return values in the conventional sense. There is a predicate called length. We could assert the length of a particular list. For instance, if we asserted that the length of this input list is 3, the fact would be true. However, if we incorrectly asserted that the length of a 3-element list is 2, the predicate would fail. In the interpreter, this simply prints false to indicate a failure, and if this was inside of another predicate body, it would cause the current branch to fail as well. But just making assertions will only get us so far. We'd like to ask the Prolog runtime what the length of this list is. Any name beginning with a capital letter in Prolog is a variable, and when a variable occurs in a predicate, Prolog will try to figure out the value of that variable using a process called unification. Here, we've asserted that the length of our list is x, but we haven't said what x is. Since it starts with a capital letter, x is a variable, so it can perform unification, which in this simple example has the effect of setting the value of the variable x to 3. Let's actually write some Prolog code, so we can see more examples of how unification works. We need a domain to model, and the classic beginner example in Prolog is family trees. So let's model part of the Harry Potter family tree. Specifically, let's talk about the Weasley family. Arthur Weasley and his wife Molly have a frankly offensive number of children. First, let's introduce the actors in this model. We'll include their genders since we're talking about family relationships, and many terms relating to family ties, such as uncle and nephew, are linked to gender. Arthur Weasley and his 6 sons are male, so we assert the single argument predicate male is true of them. Molly and their 1 daughter are female, so we write a predicate for that as well. Now we want a predicate called character, which is true for anyone in our story, male or female. We could enumerate all of the characters again, but that seems redundant given the work we just did. So instead, we'll write some rules. Everything we've written so far has been a fact. That is, we've simply asserted that something is true in the void. The claim that Ron Weasley is a male doesn't depend on anything else, it's simply true. By contrast, a rule is a fact that depends on some other facts. You can think of it as being sort of like an if statement in a more conventional imperative programming language. We'll write two rules. The first states that if someone is a male, then they are a character, and the second, likewise, states that if someone is a female, then they are a character. In Prolog, a bare name beginning with a lowercase letter is a term. A term is sort of like a symbol in Ruby or Lisp, and you can think of them as being strings with efficient equality comparison. So Ron _ Weasley is a term in Prolog. On the other hand, a bare name starting with a capital letter is a variable. A variable can be unified with a value at a later point, effectively substituting in that value for the variable. Our first rule says that for any x, whenever the predicate male is true for x, we can conclude that character is also true for x. Our second predicate, likewise, states that for any x, whenever the predicate female is true for x, we can conclude that character is also true for x. We've only just introduced our characters, but we can already make some semi-interesting queries. We can run the queries against our logical model using the sweet Prolog REPL. To load the file, we invoke the consult predicate with the file name. Now we can ask if Ron is a male, which he is. We can also ask if Ginny is a male, which she is not. We can also enumerate all of the males by leaving a variable in place of the argument. This will fill in the variable with, sequentially, all of the males it can find. We can do the same with our female and character predicates. Now let's write a non-trivial relation. Let's encode the parent-child relationship. All of the Weasley children have two parents, Arthur and Molly. So we'll write a two-argument predicate called parent to encode this relationship. Next, we distinguish between mothers and fathers. A person is the mother of someone else if they are a parent and happen to be female. So we'll write that as a rule. Then we do the same thing for fathers. Remember that names beginning with capital letters are variables. So in this predicate, child and parent are variables, which will be filled in with the actual terms that make the conditions true. Now let's encode the sibling relationship. Two people are siblings if they have the same mother and the same father. Note that we never explicitly compare any fathers or mothers for equality here. Since we use the same variable for the two fathers and the same variable for the two mothers, the Prolog unification process forces them to be the same automatically. This predicate is close, but it has a problem. Let's try to enumerate all of the siblings of Ginny Weasley. This enumerates all of Ginny's siblings as well as herself, but it's not really reasonable to say that she is her own sibling. But by our definition, she is. Ginny and Ginny do in fact have the same mother and father. So we add another condition to the end, asserting that the two children are not equal to each other. This does exactly what you'd expect. It makes the sibling predicate false if we've gotten to this point and the two variables happen to be unified to the same value. Now let's talk about how to manipulate more conventional data structures in Prolog. Prolog defines a list data type to represent linked lists, but let's create our own and work with it for a few minutes. A singly linked list stores an ordered collection of data as nodes, where each node points to the current head of the list as well as the tail, which is another list representing in turn all of the elements except the head. We'll represent the empty list, which terminates all linked lists using the atom nil. Then we'll represent a non-empty list using a compound term. A compound term is like an atom, except that it can also take parameters, and it basically functions as a rudimentary product type or tuple type to store aggregate data. In our case, we'll use the compound term cons. First, we'll define a predicate that's true for any list and false for values which are not lists. We define two clauses. First, we state as a simple fact that nil is a list. Second, we state that a cons compound term is a list if it consists of two arguments, the second of which is also a list. If we try to load this file, Prolog will warn us about a singleton variable. That is, we use the variable name h in the conclusion of our rule, but never in the hypotheses. Since we don't actually use the variable, we should replace it with an underscore, which is a pseudo-variable that acts like a different name each time it appears. Now, one of the most basic operations we might want to perform with a list is to ask for its length. Let's write a predicate that takes two arguments, a list and a number, and is true if the list is of that length. We always state predicates in terms of facts and rules that are true of them. So first, we state that nil has length 0. Next, we write a rule whose conclusion determines that a cons term, or non-empty list, with tail t has length x. This is true when t has length y for some y, and x is the successor of y. The successor predicate is true when its second argument is 1 larger than its first. With that, we can assert the length of some lists. Prolog will state that our assertion is true when we get the correct length and false otherwise. We can also replace our length argument with a variable and have Prolog fill it in for us. Now, let's write a predicate to check if an element is present in a list or not. Again, there are two clauses. Since the empty list does not contain any elements, we don't have a rule for the empty list nil. Our first fact states that x is present if it's the first element of the list. Our second clause is a rule which states that x is a member of some list if x is a member of the tail of that list. We can use this predicate to check if some value is a member of some arbitrary lists. Interestingly, if we leave the first argument as a variable, Prolog will unify it with every element of the list, giving us a quick way to enumerate the values of a list. Now let's see the syntax for actual lists in Prolog. Ordinary Prolog lists are implemented basically the same way, but the system gives us some nice syntax to work with them. The empty list is written as a pair of square brackets. This isn't actually an atom like our nil term, it's a special value baked into Prolog since lists are so common. A non-empty list can be written enclosed in square brackets with commas separating the values. To construct a list based on the head and the tail, as our cons term did before, we write the head and tail in square brackets, separated by a vertical bar. Prolog also offers us a nice syntax to prepend several elements to a list at once. The head of a list can consist of several elements separated by commas, all of which will be prepended in turn to form a new list. All of the functions we've written so far, and many more, are built into the Prolog standard library. List is called isList, list length is simply called length, and list member is simply called member. Let's write another list function, this time with the built-in Prolog list type. We're going to come up with a mechanism to append two lists together. In a functional language like Haskell, we would think of this operation as a function of two arguments, which produces a list as the result. In Prolog, we have to think in terms of predicates. So we write a predicate in 3 arguments, which is true if the third argument is the concatenation of the first 2. As with every list function we've written so far, we need a base case. The concatenation of the empty list with any list is just the latter list. Written in Prolog, we state that the list append predicate is true if the first list is empty and the second and third are equal. Next, we write a rule for the case where the first list is non-empty. If the first list is non-empty, then the result of concatenating the two lists together should begin with the first element x of the first list and should end with the result of concatenating the rest of the first list xs with the entire second list. Now this function, although it's called append, actually does several things. If we fix the first 2 arguments and put a variable for the third, we get a conventional append function for lists. We give it 2 lists and it produces, in a variable, the concatenation of the 2. If we leave the first argument as a variable, we get a function that removes a tail from the list. If the first argument is the underscore variable, which discards its value, we get a predicate that's true if ys is a suffix of zs. Conversely, if we leave the second argument as a variable, we get a function that removes a finite prefix from the list. And analogously, if we put an underscore in place of the second list ys, we get a predicate that's true if the first argument is a prefix of the third. And this is the crux of logic programming. In every other language we've worked in, functions are one-directional. We give it some input and it produces some output. But in Prolog, we write a predicate without necessarily passing judgment on which arguments are inputs and which ones are output. Then the caller decides which variables they want solved for and which they would like to provide. Our single 3-line append predicate can act as append, a prefix function, or a suffix function. Our member predicate can check for membership in a list, but it can also enumerate the elements of a list. And even the built-in list length predicate can go both ways. If we supply a list, it will give us the length, but if we supply the length, Prolog will give us a list of that length with independent variables for each element. In fact, if we want to quickly produce a list whose elements are all the same, like array.fill in JavaScript, we can do that in Prolog. Remember that everything we're doing here is still stating facts and letting Prolog figure out the values that make those facts true. This code reads as follows. There's a list xs. It has length 4, and every element of it is equal to 0. Prolog solves this equation and finds that the only possible solution is to make xs be equal to a list of 4 zeros in a row. Now let's talk about how to do some practical coding in Prolog. All of this logic is great, but sometimes, as is often the case in programming, we have to deal with that pesky thing called the real world. Can Prolog print to the screen? Or get the current system time? Or read from files? None of these are logical operations. They all carry side effects. There's no logical model for reading from a file. So let's take each one in turn. Printing to the screen is done with the write predicate. The write predicate takes one argument and is true. It simply succeeds for all argument. From a purely logic-oriented perspective, it's a fairly useless predicate. But that's not the point. When the write predicate evaluates its correctness, it also has the side effect of printing its argument to the console. So when we put write in our code, it has the effect of looking like a print function, even though it's really a predicate that happens to carry side effects when it evaluates. Likewise, we can get the current system time with the getTime predicate. GetTime is a predicate of one argument which succeeds if the argument is a representation of the current system time. If we feed it a number, the predicate will only succeed once in a blue moon if we happen to guess the number correctly and run the predicate at the perfect fraction of a second. More likely, we'll invoke getTime with a variable and let Prolog fill in the value. Now what does this number represent? Prolog represents the current system time as the number of seconds since the Unix epoch, or January 1st, 1970. We can print this in a variety of formats using the 3-argument predicate format time. Format time takes a destination stream, a format string, and the time. So we could write this, for instance, to print the current time in the format prescribed by the ISO 8601 standard. By now, I hope you're seeing how Prolog predicates are used as a very broadly applicable tool to solve all sorts of problems, even those that don't immediately fit into a conventional logic-oriented framework. Now let's talk about file I/O now. In Python, we open a file with the open function, then read from it using one of several methods. Finally, we close the file using close. The approach is very similar in Prolog. The open predicate takes 3 arguments and is true exactly when the first argument is a file name, the second is the file mode, and the third is a stream handle. As with many of these predicates, open is intended to be called with variables. Specifically, the stream handle argument must be a variable. The open predicate succeeds and, as a side effect, opens the file and unifies the file's stream handle with our variable. The file mode shall be one of read, write, append, or update. The first 3 work similar to the equivalent modes in Python. Read opens the file for reading, write truncates the file if it exists and opens it for writing, append opens the file for writing but starts at the end if it already exists. Update is an interesting one. It opens the file and starts writing at the beginning, but it doesn't truncate the file. So we simply overwrite the existing contents on an as-needed basis. In our case, we'll read from the file. Once we have the handle, we can read from it using readString. ReadString is a predicate of 3 arguments. The first is the stream handle we got from open. The third is the resulting string, as an output argument. Once again, we usually give a variable for this argument and let Prolog fill it in for us. The second argument is an interesting one. The second argument is the number of characters read in from the file. If we give an underscore, Prolog reads the rest of the file. If we give a variable, then Prolog still reads the rest of the file and unifies the variable with the number of characters actually read. However, if we bind that argument to a specific number, then Prolog will only read that many characters in order to make the predicate true. Finally, when we're done with the file, we should close it with the close predicate. This predicate takes 1 argument and closes its stream argument as a side effect. Now would be a good time to interject briefly about the difference between strings and symbols. I've been using double quotes and single quotes in different places, and in Prolog, they mean different things. We've already discussed atoms, which are like Lisp symbols and act as immutable intern strings that stand for themselves. You can think of them as being sort of like an enum, but without a finite set of values to pull from. Atoms make sense when the thing you're representing exists as a unique, well, atom, more so than being the sum of the characters making it up. It made sense to use atoms for our Harry Potter characters, since each of them is a distinct entity that exists, not merely the sum of the characters in their names. Likewise, the file modes we can pass to open are read, write, append, and update. These are 4 distinct modes, sort of like an enumeration, so we use atoms there as well. Text enclosed in single quotes also forms an atom. That is, there's no difference as far as Prolog is concerned between the name Ron Weasley written out and the name Ron Weasley enclosed in single quotes. However, single quotes also allow us to write atoms that are not valid Prolog identifiers, such as atoms containing parentheses, spaces, or other exotic characters. Double quotes, on the other hand, construct strings, which work like strings do in most programming languages. They're sequences of Unicode characters. We read the contents of a file into a string, for instance, since the contents of the file are actual textual data, not just an entity that exists in the abstract like an atom. Conversion between strings and atoms is done with the 2-argument predicate atom-string. This one predicate does both conversions. We can supply either argument and leave the other blank to convert in whichever direction we prefer. Finally, note that strings are not lists. They're an efficient representation of sequences of Unicode characters. If you enclose text in backticks, then that will be read as a literal list of code points. Text enclosed in backticks actually is a list of integers representing the code points of the characters. Let's write some more practical code. We're going to write the command line tool grep in Prolog. Our simplified grep command will take 2 arguments, a regular expression, and a file name, and will print to standard output every line of the file which contains a match for the regular expression. We'll use the built-in PCRE library to actually perform the regular expression matching. PCRE stands for Perl Compatible Regular Expressions and is a very powerful regex library with bindings available in many languages. So we start with a use module predicate invocation. Now we haven't actually discussed how to specify a sort of main function in Prolog. When you run the interpreter with a Prolog source file name as argument, the interpreter will start by evaluating any rules that have no conclusion. So if we want to write a main predicate, we simply start with :/ and put our main code inside of that clause. Now let's write our grep program. The main program flow will be as follows. First, we read in the command line arguments to get the regular expression string and the file name. Then we compile the regex. Recompile is a PCRE predicate that compiles the string into an automaton that can efficiently check for matches. Next, we read the file line by line into the lines variable. Finally, we output the lines that match the regex and then exit the Prolog interpreter. Read file lines and write output are predicates we'll write in just a moment. Let's start with read file lines. This predicate takes 2 arguments, the file name and a list of strings. It should be true if the file contains exactly those lines as strings. First, we open the file for reading, saving the stream into the in variable. Then we read the whole file into content. Since we haven't specified a length, read string implicitly reads until the end of the file. Next, we close the stream since we're done with it. And then we call split string to split the contents into a list of strings delimited by new lines. Now for write output. This predicate takes two arguments, a regex and a list of strings. It succeeds, and it has the side effect of printing out the lines which contain a match for the regex. First, we call the include predicate, which is Prolog's list filter operation. It takes a goal, an input list, and an output list. The output list consists of the elements of the input list for which the goal is true. Rematch is a two-argument predicate, which takes a regular expression and a string, and is true if the string contains at least one match for the regular expression. Include, in turn, expects a goal in one argument which it can apply to each element of the list to determine which ones to keep. Prolog allows us to curry this two-argument predicate into a single-argument one by supplying the first argument up front. Finally, we use maplist to map the writeLine predicate over the matching lines. WriteLine does exactly what it sounds like. It writes its argument to standard output, followed by a new line. We can run this with some sample input to test it. There's one more little modification we can make. Many programming languages offer a way to safely open files in such a way that, if the code that interacts with the file fails in some way, ensures that the file will still be closed. Python has with statements, Ruby has an optional block argument, and Java has the try with resources statement. Prolog has a similar feature. Setup call cleanup is a meta predicate that takes three arguments, a setup, a goal, and a cleanup operation. It runs the setup, then the goal, and finally the cleanup. If the goal fails for any reason, we still run the cleanup before failing. In our case, setup is open, our goal is to read the string, and our cleanup is close. This runs like the original program, but is safer in the event something catastrophic happens during file access. Now let's take another look at our solution again. The actual computation here is fairly simple. The complicated part is the dynamic programming bit. We could spend the next 10 minutes figuring out how to code a mutable dictionary in Prolog and keep track of a cache variable, but we don't need to do that, because Prolog already has a tool built in for this, and we've been using it the whole time without even knowing it. All of the facts and rules available in our program are stored in the Prolog knowledge base. Normally, we add information to the knowledge base by writing additional code that provides data to Prolog. However, we can also do so dynamically at runtime, and we're going to do exactly that, using Prolog's knowledge base to perform dynamic programming. For efficiency reasons, if we want to dynamically add data to the knowledge base, we have to declare up front that the predicate is dynamic. Dynamic is a special directive, not a predicate. Now we write a recursive grid predicate to calculate the number of paths through an n by m grid. First, our base cases, which are simple facts. If the grid has width 0, then there's only one path, namely the path produced by going down repeatedly. Likewise, if the grid has height 0, there's still only one path, given by going right repeatedly. Now, our recursive rule. Phrased as a predicate, it is true that there are x paths through the grid of size n by m if the following is satisfied. Let y be the number of paths through a grid one narrower than n, and let z be the number of paths through a grid one shorter than m. Then the total number of paths x is equal to y plus z. Is a very special predicate in Prolog, in that it's uniquely unidirectional. Is, unlike many of the predicates we've used so far today, only works if the second operand is ground, which is a fancy way of saying all of the values are known. Basically, that means we know the values of any variables in that term in advance. We can't use it in reverse to solve an equation given a result, but we can use it to calculate math given all of the values. Now we've written a recursive predicate, but we want to cache the results in the knowledge base so we don't have to recompute everything all the time. To add information to the beginning of the knowledge base, we invoke the assert a predicate. We want to add these facts to the beginning of the knowledge base so that Prolog sees them before it sees our recursive rule, or else it defeats the point of caching the results at all. Finally, our main predicate invokes grid for a 20 by 20 grid with the number of paths bound to a variable x. Then we display x, and that's it. That's the whole program. This Prolog file runs instantaneously and produces the answer we're looking for. And this solves Project Euler problem number 15 in Prolog. We're done with the Project Euler portion of the video, but I have more to say on Prolog. If you want a more behind-the-scenes look at how Prolog actually evaluates predicates, check out the companion video I'll be publishing alongside this one. Aside from that, tune in next time when we solve Project Euler problem number 16 in Labyrinth, the maze-oriented programming language of rapidly shifting walls.